So changes in pH also affect the solubility of many slightly soluble ionic compounds. So if we think of chapter 14 information, remember that the anion of a weak acid is its conjugate base and has the ability to react. And of course, vice versa if you had a weak base, right? Now, if you were to add H3O plus from a strong acid, what's going to happen? Well, guess what? We're going to see how the adding H3O plus from a strong acid will actually increase the solubility of a salt. And so we're going to be using Le Chatelier's principle to help us explain why, and of course our understanding of acids and bases and how their ions work in salt solution. So we're going to use calcium carbonate Professor X as an example. Now Professor X has powerful telekinetic abilities, and of course he can read minds, but they do have their own limits. Just like calcium carbonate only slightly dissolves in equilibrium. So here's the dissolution equation for calcium carbonate. It's a solid that's going to be in equilibrium, or it's going to be in a saturated solution to produce Ca2 plus ions and CO3 2 minus ions. To figure out the effects of pH, we first have to understand whether or not these ions will react in solution. So Ca2 plus is coming from a strong base. We know it's not going to react in solution, but CO3 2 minus is the conjugate base of a weak acid. And so because it's the conjugate base of a weak acid, it can definitely react. And so if I'm going to add a strong acid to this overall solution, okay? So we have this solution that's saturated of our CaCO3, and of course we have the Ca2 plus ions, and of course the CO3 2 minus ions. We said our CO3 2 minus ions will react if we continually add H3O plus to our solution. And so now we have our base here, we have H3O plus. If it's a base, it's going to accept a proton. It's going to accept a proton from H3O plus and form HCO3 minus, and of course water. And so automatically, if it's forming HCO3 minus, that means it's going to be removed from the overall reaction as it's being used up to form this new species. And this HCO3 minus, if we continually add H3O plus, will then act as a base and actually again react with H3O plus itself. And so when this H3O minus acts as a base and reacts with H3O plus, it's going to form H2CO3 or carbonic acid. Now this is going to be a transitionary state, meaning it's going to decompose really quickly. And it's going to decompose into water and CO2. Okay, folks? And so CO2 is going to be something that shows bubbling. And of course, water is simply going to be water. Therefore, if we continually add a strong acid to this calcium carbonate solution that's saturated, guess what's going to happen? Our solubility is going to increase. Because we are decreasing this potential, this overall aqueous ion here, that's going to force the overall equilibrium to shift to the right, and that's going to increase solubility so that we can produce more of it to get back to equilibrium. Okay, folks? And this understanding allows us to have a lot of different field tests. So for example, there is a qualitative field test you can use by just taking HCl and treating it with carbonate minerals. And if it does bubble up, then you know that you are dealing with that carbonate ion. And so here's an example of that carbonate ion or a piece of carbonate mineral being mixed with HCl. And as you can see, there's a lot of bubbling to show that it is producing that CO2, as this H2CO3 or carbonic acid is also being produced. So overall, let's go ahead and look at it. We have our CaCO3 is going to, of course, dissolve into these two ions here. This ion is going to react with H3O plus and form HCO3 minus. So therefore, we're decreasing this ion here. If we continually add strong acid, it also produces H2CO3, which then breaks down to CO2, water, and we're still left with the Ca2 plus ion that again does not react. And so because we're decreasing a product, we're then going to shift to the right so we can produce more of that product and replenish it to equilibrium. Now for this analogy, I always say, okay, for us, we use Jean Grey, and we use H2SO3 for Jean Grey, so we can just say that this is now H2CO3 like our example, and this will be HCO3 minus like our example. Now essentially, when Phoenix is formed, right, all the X-Men or even Marvel characters around, and we're going to focus on X-Men, we want to make sure that Phoenix does not go to Dark Phoenix, right, and ruin everything. And we also want to make sure that Phoenix themselves, the Phoenix Force, is controlled in some way. And so a lot of times you saw a lot of different X-Men characters will always come to Jean Grey's aid to try to make her calm down in some way to get back to normal. And so one of the people who would do that would be Professor X. And so calcium carbonate Professor X is actually going to break themselves down, as we see here, and increase solubility so that HCO3 minus Phoenix can H2CO3 Jean Grey, and again release CO2 and water, thereby neutralizing the Phoenix force and going back to normal. Now let's go to the Avengers compound and see a real example of the effects of pH. So here we're predicting the effect of solubility of adding a strong acid. It says write a balanced equations to explain whether addition of H3O plus from a strong acid affects the solubility of each ionic compound. And they give us these 3 ionic compounds to write. Now, as you can see, this is all nomenclature. So we definitely have to get our formulas, and then once we have our formulas, straight to writing our dissolution equations like I have done for letters A through C. Also, when I think of a strong acid, I automatically write H3O plus just to get my mind working. Now, we saw previously that in order to see the effects of solubility when you add a strong acid, we need to be having a strategy to focus on the anion of a weak acid. So when I got all of my letters kind of written down, all of my dissolution equations, the next thing I want to do is focus on the aqueous ions that are produced. And then of those aqueous ions, I want to focus on the conjugate bases or anions of a weak acid or a base in general, because I know that base has the ability to react with that H3O plus. And if it reacts with that H3O plus, what happens? It means it's going to be removed from the overall equilibrium system. And if it's removed from the equilibrium system, then molar solubility is going to decrease, and therefore the equilibrium is going to shift to the right to again try to produce more of that ion again. So for letter A, we have lead 2 bromide, which is PbBr2. Here's the dissolution equation, which is going to be Pb2 plus and 2Br minus. Next, we have our copper 2 hydroxide, which is CuOH2 solid, in equilibrium to form Cu2 plus and 2OH minus. And finally, for letter C, we have iron 2 sulfide, which is simply FeS solid, in equilibrium to form Fe2 plus and S2 minus. Next, for this type of question, you want to find the anions of a weak acid. So when I'm looking at Pb2 plus, I know I'm not going to form or focus on any cations. And the reason why is because metals are more complicated. If we even go back to our understanding of certain metals, we know they have to be a certain size, shape, and so because they're so varied, it can be difficult to come up with certain specific rules we can go with. So again, we focus on the anion of a weak acid. Now, with letter A, we know we're not dealing with Pb2 plus, so we're looking at Br minus. Br minus is a conjugate base, but it's actually a conjugate base of a strong acid. And so because it's the conjugate base of a strong acid, it's going to have no effect on the solubility, but it's not even going to react with the H2O plus. Now let's move on to letter B. As you can see, we have 2 OH minus here. Will OH react with H3O plus? Yes, it will. So if you have OH minus, and of course you're going to react it with H3O plus, you're going to end up forming H2O. Okay? And so because you end up forming H2O, you're going to end up using up this 2OH minus. And so when you use up that 2OH minus, what's going to happen? The equilibrium has to shift to produce more of it. So the equilibrium will shift to the right here. And if the equilibrium is going to shift to the right, that means we are going to increase solubility, just like we saw before in our information. And finally, we have FeS, which is going to be in equilibrium to form Fe2 plus and S2 minus. Now we don't focus on the Fe2 plus, so let's focus on S2 minus. Is it the conjugate base or the anion of a weak acid, or is it a base in general? And the answer is yes, it is the conjugate base of the weak acid, HS minus. So what we can do is take our weak base, mix it with H3O plus, and we're going to end up forming HS minus and of course water. And because the addition of that strong acid is removing S2 minus from the overall equilibrium system, it's going to therefore increase solubility, and we're going to have a shift to the right for this equilibrium system itself. All right, on to the next concept.